All right, so picking up here in part 2 of our chapter 1, section 1 video, we are looking at the vertical line test. And so what the vertical line test tells us that is that if we have a graph of a relation and we are able to draw any vertical line through it, and those vertical lines all only touch once or don't touch at all, the graph of the relation, then that means that relation is a function. Now, if even one vertical line, if every vertical line is totally okay, only touches once, but there's even one single vertical line that touches more than once, then that means it's not a function. So let's take a look at what that looks like with some graphs. And we have some graphs here. Your notes may not have these filled in yet, so you might want to pause the video here and just draw all the graphs real quick. But what we're going to see here in these examples is displaying the vertical line test. So in this first one, we have a parabola. And if I draw vertical lines over here, if I draw vertical lines here, every single one of those vertical lines only hits my graph one time. So that means f of x is a function. And maybe I should just go ahead real quick and label all of these f of x. And the reason I want to make sure they're labeled is because in a minute here, we are going to look at the horizontal line test, and that'll tell us information about the inverse of f of x. So if I look at this next graph, a vertical line out here is totally fine. A vertical line here where it just touches the edge and only hits one point is totally fine. But as soon as I have a vertical line that hits 2 points, that tells us that f of x is not a function. Now, if I was phrasing this as a yes or no question, this would be a yes, this would be a no, which is kind of how I have it phrased here. So in the next example, a vertical line out here is totally fine. Over here is totally fine. But this one vertical line, and it only takes one, hits at every single point. Not only does it hit more than once, it hits at every point. So that would tell us that f of x is not a function. And in the next one, all of these vertical lines are totally fine. A horizontal line is totally fine. Every single one just hits one time. So I'm going to go ahead and switch to answering yes or no questions. So I'll say yes, it is a function. And the next one, vertical lines, every single vertical line only hits once. So yes, it is a function. And even though this looks like kind of a funky graph, every single vertical line, even where it gets really steep, only hits my graph at one point. So yes, it is a function. Now, I mentioned briefly that we are going to kind of talk about inverses a little bit. What is an inverse? It's where the domain and range switch. So these are special types of functions. Again, we'll investigate a little bit deeper further on in this chapter. But the short answer is that our domain and range switch, or our variables switch places. And so if we were solving this algebraically, we would switch x and y and then solve for y. Here, if we have a set of points, we can see that if we have f of x equaling these points here, if we switch the x and the y, so it becomes 4, 3, that would be the inverse. So all of these points switched, you can see becomes the inverse there. And what the horizontal line test tells us is information about the inverse of the graph we're looking at. So this test does not tell me information about the graph I'm looking at. It's telling me information about the inverse of this graph. So here, if we draw a horizontal line through these graphs and it hits more than once, then that means the inverse is not a function. We're not looking at the inverse. We're looking at the original function f of x. But we're finding information with the horizontal line test about the inverse of this function. So all of these horizontal lines all hit just once, and that tells us that inverse f of x, that's this notation here with this -1, that's referring to the inverse is a function. Right, and Horizontal line down here is okay. Horizontal line right through the vertex is okay. But as soon as I have a horizontal line that hits more than once, that means inverse f of x is not a function. And here we saw in the last examples that this failed the vertical line test, but it passes the horizontal line test just fine. So that tells me that the inverse of this function is a function. And though we saw this type of example pass the vertical line test, it does fail the horizontal line test. So inverse f of x is not a function. And here this would pass the vertical line test, but it fails that horizontal line test, even though it would pass here or maybe down here. It just takes one line to fail. So that means that inverse f of x is not a function. And then here, horizontal line test all just hit once. So I can just say yes, I suppose. Inverse f of x is a function. All right. Now, we've gone over the vertical line test and the horizontal line test. What about both of them? So there are a special set of relations that are referred to as one-to-one functions. And what this means is that they pass both the vertical line test and the horizontal line test. So what this means, if we were to look at like a set of points, both the x's and the y's don't repeat. So every member of the domain maps to exactly one member of the range and vice versa. So checking if this passes the vertical line test, it does. Checking if this passes the horizontal line test, and nope, it fails. So that means that this is not one-to-one. Okay. And the next one, it passes the vertical line test. Even though it gets really steep in a few areas, it still only hits it exactly one. For both, it passes both. So that means that this is in fact 1, 2, 1. Or it's a one-to-one function. This fails the vertical line test, so I don't even need to check the horizontal line test. But just for consistency, I'll go ahead and do it. It passes the horizontal line test. It fails the vertical line test. But since it doesn't pass both, it is not 1, 2, 1. All right, let's check these sets of points here. My x's, let's see if they're all unique. 3, 5, -2, -1. Those are all different numbers. 4, 7, -1, -3, or +3. Those are all separate numbers as well. So that tells us that this is 1, 2, 1. Now, notice that I have a 3 here in the x and I have a 3 here in the y. That's okay. But what's not okay is if I had a 3 here in the x and then the 3 here again in the x. Or if I had a 4 here in the y and then a 4 here again in the y. Having one x, that's a 3, and having one y, that's a 3, that's okay. 2, 4, 3, -1, those are all unique. 3, 7, 8, 0, those are all unique. So these are both 1, 2, 1. All right, so this next section is going to get us into factoring. And we are going to look at a couple different methods for factoring. The first one we're going to look at is factoring by grouping. But before I get into that, one of the things that I want to make sure that you do every single time you factor is to always pull out the GCF first. So any time we factor, we always want to pull out the GCF, or the greatest common factor, first. Let me zoom out a tad here to make sure I'm not missing anything. Okay, so anytime we're factoring, that's what we want to do first. So in this first example, I have four terms. Factoring by grouping is the method that should come to mind when you have four terms. Okay, so if you have four terms, it doesn't mean that everything with four terms that factoring by grouping will work, but that's what should come to mind as the method to try. So factoring by grouping is exactly what it says in the name. We're going to group, and what I should have done first is see, is there a GCF among all four terms? No. The first three have an X, and the last three have a common factor of 2, but there's no common factor among all four terms. So then getting into factoring by grouping, we group the first two and we group the second two, or the last two. And now what I'm going to do is in these groups, I'm going to look, do these two terms have a common factor? Yes, I can pull out an x squared and I'm left with x plus 6. And in these second two, do they have a common factor? Yes, they have a common factor of -2, and I'm left with x plus 6. Now, if you're not sure if you have the signs correct or anything like that, you can always check, okay, if I distribute the -2 back in, do I get where I was? Well, yeah, -2 times x would give us -2x. -2 times +6 would give us -12. Now I notice that this term and this term have a common factor of x plus 6. So I'm going to pull this x plus 6 out front as a common factor. And what I see a lot of students ask me at this point is, well, shouldn't it be x plus 6 squared because there were two of them? No. Just like here where we saw they had a common factor of x squared, I didn't pull x to the fourth power out. I just pulled out x squared, the common factor. And here I didn't pull out two twos, I just pulled out a 2, which was their common factor. This whole term here and this whole term here have a common factor of x plus 6, so I pulled it out. And what's left is this x squared minus 2. And that's what's left there. So that is factoring by grouping. That's the whole process right there, is grouping the first two terms and the last two terms, finding their common factors, seeing that what we have here in parentheses is the same, and then bringing down what's left over. Now, you'll see some examples where maybe what's left over we could factor further, or maybe you get what's in parentheses here is not the same, and then we can't use factoring by grouping. So there are variations of problems with four terms, but that is an example of factoring by grouping. Now, this next example is factoring using what I call is the X method. And this is how I will factor things all class, like all semester long. If you have learned how to factor something like this and you see this polynomial right here and you're like, oh, that's no problem. I can totally factor that. I could factor that in my sleep. Great. Go ahead and factor the way you have normally been factoring up to this point. But if you see that and you're like, I've seen multiple methods for factoring something like that, and I think I could probably figure it out, but I don't remember exactly how to do it, you need a go-to method for factoring before you get to calculus. So if you don't have one, I really like this method. You are welcome to establish this method. But by the end of really this chapter, but worst case scenario, by the end of this class, you should be able to factor something like this nearly in your sleep. Like it should be mastered, not just I can do it. It should be, you should be a pro at factoring. Because in calculus, this will be a much smaller part of much larger problems. So in general, these kinds of polynomials here, anytime we are factoring, again, like we just talked about, you always want to pull out the GCF first. And I noticed that these have a common factor of 2. And then what I'm left with is some smaller numbers in here. And when I'm factoring something of this form, the general form for a polynomial or a trinomial like this is ax squared plus bx plus c. And I'm going to use this x here. Now, you've probably seen some factoring methods that use this x. Up top, we're going to put our a times c value. And then on bottom, we're going to have our B value. And what I'm looking for is two numbers that multiply to this top number and add to this bottom number. So in the example we're looking at over here, I have 3 is my A and -5 is my C. 3 times -5 is -15. And my B value is -2. Now, 15 is a relatively small number, so we can think about what multiplies to 15. Well, that's 1 times 15 and 3 times 5. And those are my only options. And if it multiplies to a negative number, I know I'm going to have one positive and one negative. Well, my numbers are going to be 3 and 5. And if I put the negative on the 3 and left 5 as positive, then those would add to a positive 2. So I have to put the negative on the 5 and have a positive 3. Those add to -2 and then multiply to -15. Now, up to this point, this probably looks like methods you've seen before, but here is where my method will maybe differ a little bit from how you've seen it before. At this point, I take these two values, carrying my greatest common factor here, and I'm going to put, I'll do it in general over here, AX plus one number and AX plus the other number, and I call this step taking out the trash. It's kind of a catchy thing. Hopefully will help you remember this step here because this is the step that some students forget. If you have an A value of 3, then I'm going to put 3x here and 3x here. Now, if I were to leave both of those in there and I were to check my answer and multiply 3x times 3x, I'd get 9x squared. So I know that there's an extra 3 in there. And the way I find where that extra 3 is one of these, or possibly both of them, will have a common factor. And I see here that in this set of parentheses, I have a common factor of 3. Now, that's not a common factor I'm pulling out. That's the 3 that should never have been there in the first place. So I end up with x plus 1 and 3x minus 5. Now, the nice thing about factoring is you can always check your answer. The easy way to check your answer is either FOIL or box method real quick and make sure that you did it correctly. So I can multiply x plus 1 and 3x minus 5. 3x times x is 3x squared. 3x times 1 is 3x. X times -5 is -5x, and -5 times 1 is -5. I get 3x squared, -5x, and 3x is -2x minus 5. And then multiplying times my 2, I end up with 6x squared minus 4x minus 10, which is what we started with. So I know that I did, in fact, factor this correctly, and this is my answer. If you have another method that you like that works for you, you are welcome to use that. But I like this method because if this is factorable at all, this method will work. So this is what you will see me use throughout this course. And then we also have special factors. Now, if you're moving on to Calc 1 after this class, you will be expected to know these special factors just randomly. You may not have a warning that you're going to be going over this, but you'll need to know it. So here it says factoring using special factors. Difference of two squares is probably the one you've seen the most. That's something like x squared minus 9, and that would be x plus 3 and x minus 3. The sum of cubes and difference of cubes formulas are probably less common to you, but you'll notice that these two formulas look almost exactly the same. I call these two formulas the same, opposite, plus formulas because you'll see it's A, B, A squared, AB, B squared, B squared. The only thing changing are the signs. So if you have a sum of cubes, then you're going to have the same sign, the opposite sign, and a plus sign. If you have a difference of cubes, you're going to have the same sign, opposite sign, plus sign. So that's how I remember where the signs go, and then just have to memorize essentially one formula. Now, in these next examples, we're not just factoring, now we're also going to solve. And anytime you are solving a polynomial equation, the first thing you want to do is get it into descending order. Descending order is largest exponent, next largest exponent, and so on. So I'm going to put negative x cubed minus 4x squared plus 9x plus 36 equals 0. And this is four terms. So as we said, four terms, I should be thinking factoring by grouping. And you know what? Before I actually do that step, I notice that I can actually pull out a GCF. So let me go ahead and get rid of those parentheses here real quick. And we're going to factor out a common factor of -1 because I'd also like my leading term to be positive. And now I'm ready to use factoring by grouping on this inside part here. So I'm going to keep this -1 kind of out front and it'll get carried along for a bit. In this first group, I have a common factor of x squared and then I have x plus 4. And then in the second factor, I have a -9 as my common factor. And then I'm left with x plus 4. And again, you can distribute to make sure you get back to where you started. And I notice that we have this common factor of x plus 4. So carrying my -1 down, I've got x plus 4. And then what I'm left with is x squared minus 9. Now I notice here that that's actually a difference of squares, so I can factor that one further. Let me move my work up here. And I have -1 parentheses x plus 4, and that x squared minus 9 is going to become x plus 3 and x minus 3. Well, this is completely factored now. I can set each of those factors equal to 0. And when I do that and I solve, x will equal -4, x will equal -3, and x will equal +3. So we have 3 solutions here. All right, the next example, we also want to make sure that these are set equal to 0. So before I can jump into factoring or even looking at our GCF, I need to get this set equal to 0. So I'm subtracting 60x onto the other side. And now I notice that these have a common factor of 6x. And when I pull that out, I'm left with 3x squared minus x minus 10. And now I can go ahead and use the x method for what's inside here. My a is 3, my c is -10, so -30. My b value is -1. Well, there's actually lots of things that multiply to 30. 1 times 30, 2 times 15, 3 times 10. It's not divisible by 4, but 5 times 6 also gives us 30. Now, 5 and 6, I think, are what's going to give us this -1 here. We know we're going to have a positive number and a negative number because they multiply to something that's negative. And we're going to have a -6 and a +5 because those add to -1. So this next step, again, we call taking out the trash. So 3x, my a value, minus 6, and 3x plus 5 equals 0. And I have that 6x out front still. That was my GCF. And here is my trash. That 3 shouldn't be there. So 6x times x minus 2 and 3x plus 5 equals 0. And I get x equals 0 from here. I get x equals 2. And x equals -5 over 3. And those are my 3 solutions. The next one's setup is very similar. We need to get it set equal to 0 first. And so we're going to go ahead and set this equal to 0 by adding 15a squared to both sides. So adding that over, I end up with 6a cubed plus 15a squared minus 36a equals 0. And I notice that I have a common factor of 3a. So 3a can be pulled out, and then I'm left with 2a squared plus 5a minus 12. And then I can go ahead and use the x method for what's inside here. A times c is negative 24. My b value is 5. And thinking through what multiplies to 24? Well, 1 times 24, 2 times 12, 3 times 8, and 4 times 6. So 3 and 8 it multiplies to a negative, so one of those is going to have to be negative, and it has to be the 3 because I need them to add to a positive 5. So then going into the taking out the trash step, 2a minus 3 and 2a plus 8. And my GCF is still there. There's the trash here, and I have 3a times 2a minus 3 times a plus 4. And again, you could always multiply these out and check your answer. So from 3a, we get a equals 0. From 2a minus 3, we get a is equal to 3 over 2. And then from a plus 4, we get a is equal to negative 4. All right. One last problem in this section. The setup is a little bit different, but it's actually the same type of problem as what we were just doing. Here it gave us some function f of x, and it says to find where f of x equals negative 15. That is not plugging 15 in. That's setting f of x equal to negative 15. So 2x squared minus 7x equal to negative 15. Well, I can add 15 to both sides, and I get 2x squared minus 7x plus 15 equals 0. There's no GCF, so I can jump straight into the x method. 2 times 15 is 30, and then I have negative 7. 1 times 30, 2 times 15, 3 times 10, and 5 times 6. So this is going to give me negative 10 and 3. Taking out the trash, 2x minus 10 and 2x plus 3 equals 0. Trash step here, and I have x minus 5 times 2x plus 3. And that gives me x equals 5 and x equals negative 3 over 2. And that is where f of x equals negative 15. And that brings us to the end of part 2 of section 1.